So at this point, we are very good at finding the area under a positive valued function and above the x-axis. What we want to look at in this section is how we find the area between two curves. And as you'll see very soon, I hope, the answer has everything to do with the way we think about our rectangles. So let's look at a picture. So here we've drawn two curves, and we want to find the area between them. Oh, let's say between here and here. Now, we've seen before how rectangles can help, because if you get these rectangles skinny enough, they'll be a pretty good approximation. So the way we want to draw these rectangles is some like this, some like this, and some like that. And the big question that I want you to think about is this. In each case, what is the height of the rectangle? Now we sort of have three cases here. In this case, both functions are positive valued. In this case, one function is positive and the other is negative. And in the last case, both functions are negative. And so, are there three different cases for the height of the rectangle? And I'll let you think about that for a second. And why don't you pause and think about how you get the height, and we'll be right back. Did you get it? Did you see that it really doesn't matter whether the functions are positive or negative? All that matters is which function is above the other one. Whether they're both positive and one negative, or both negative, if you subtract the top minus the bottom, it will always be a positive valued expression. And that's the simple answer for this problem. And so if we say that this is A, x equals A, and we say that this is x equals B, then the area that we're looking for is just the integral from A to B of top minus bottom. And this is a particularly easy example because f is always above g. In the case where functions might change which one is on top and which one is on bottom, you have to find where that point happens. And there'll be plenty of examples like that. But this is the heart of the whole problem, is just looking at the top minus the bottom and then integrating. So off we go to some examples. So here's a typical example. We want to find the area bounded by, in other words, enclosed by these two graphs. And as always, we want to look at a picture of what we're talking about. So y equals x squared is something like that. Y equals square root of x looks like that. And so the area that we're interested in finding, let me change colors, is right in here. So that's what we're trying to do, find that area. And what's nice is from here to here, from the whole area of boundary, square root of x is always above x squared. And so we do have to find the point of intersection, and that's 1, 1. You should be able to figure that one out without too much difficulty. Sometimes, however, that kind of problem, finding this point of intersection, can only be done with a calculator. Okay, so now let's do the work. This area is going to equal the integral from 0 to 1 of top minus bottom. And why don't you take a second, pause, and see whether you get the correct answer. And the correct answer, after you do all the little computations, is equal to 1/3. Did you get it? Okay, we do have another example coming. Let's hold on and do that one. So here's a good problem, and we'll see how we can approach it from different ways. But here we want to find the area bounded by the square root of x, x minus 2, and the x-axis. So I'll give you a picture very shortly. Here we go. So here's the picture, and I can't emphasize how important it is to always think about rectangles. And if you do that, if you think about the rectangles here, what you notice is that we have two different cases. Sometimes the rectangles would look like this, but other times they look like this. And so we essentially have to break this up into two cases. And here's the kind of the demarcation line. So therefore, what we have for our expression for the area is two integrals. First, we're going to go from 0 to 2, and then we're going to go from 2 to 4. And from 0 to 2, it's top minus bottom. So just to emphasize it, I'll write that as the square root of x minus 0, because this is the bottom line, which is the x-axis. dx, and then from 2 to 4, it's top minus bottom, x minus 2 dx. Okay, so this isn't that hard, although we recognize when we think about the rectangles that we need two cases. What I'd like to suggest to you is that it actually might be a simpler problem if we think about our rectangles going the other way. In other words, if we think about rectangles going from right to left. And in that case, regardless of where I draw them, what's on the right and what's on the left will always be the same. So we'll go on to one more slide and we'll show you what that looks like. So here's the same picture. But instead of top minus bottom, we're going to go right minus left. And that'll give us the length of that. The little bit of width is no longer dx, it's now dy. We're no longer integrating from, let me get it in there, from 0 to 4, we're integrating from 0 to 2. So everything is going to turn 90 degrees. And we no longer want to describe our functions in terms of y equals, we want them in terms of x equals. So this function is x equals y squared, and this function is x is equal to y plus 2. And again, this is my little dy right there. And so I'm going to be adding up these rectangles from bottom to top. And so in that case, what I get is, for my area, just one integral. I'm going to integrate from 0 to 2, because I'm going up to 2 for the y. And it's going to be right, which is y plus 2, minus left, which is y squared dy. And that is actually an easier expression to integrate than the previous one. And what you'll see in this chapter and beyond is you'll no longer be asked really to do this integration. At this point, we assume that you can do something like that, and really the true creative difficult work is in coming up with the definite integral that gives us what we want. We've seen that we can actually deliver a definite integral like this to our calculator and get a perfectly fine answer. So there we go. That's the end of this lecture. See you next time. Have a good day.